Hi, I'm Callum McCurry, and today I'm going to be talking about a joint work with Alan Borg and Akash Raheja. And the title of this paper is Profit Matching in the Probe Commit Model. Okay, so what exactly is the problem I'm going to be talking about? Well, you can consider a setup where there's an offline seller, which has a collection of indivisible items, U, which they wish to sell to unit demand buyers. So in other words, every buyer wants at most one item. Each buyer is going to be specified by edge weights, edge probabilities, as well as an integer patience, LV, and we'll refer to G as a stochastic graph. Now, each edge has a state, which is active independently with probability PUV. And here, an edge is active, then it means that U can be sold to V or otherwise matched. And WUV denotes the revenue gained upon such a transaction. Okay, so initially, all the states are unknown to the seller. And the seller adaptively probes edges where for each buyer V, at most LV adjacent edges can be probed. Finally, the matching decisions have to respect commitment. So what does it mean? It means that if the seller probes an edge and it learns that it's active, then it has to be added to the current matching or discarded forever. All right, so let's see what this looks like. So you can imagine I first probe the first item and the first buyer, and then I learn that the edge is inactive, so I can't add it to the matching. I then probe another edge. I learn that it's active, and I decide to match now the second item to the final buyer. Once again, I probe another edge. I learn it's active, and now I'm actually able to match the first buyer to an item. And finally, I look at my first item. I check, okay, let's probe the instant edge to the second buyer, and I learn that it's inactive, so I can't add it to the matching. Okay, so the output then of the seller is going to be the matching, so these green edges. And if we denote its total revenue by W of M, then the goal of the seller is to maximize the expected revenue of the matching. So from now on, we'll sort of refer to an offline seller strategy as an offline probing algorithm. Okay, so in this paper, we're actually going to be interested in algorithms in the online setting. So in this setup, the online single seller, or otherwise known as an online probing algorithm, they have limited information regarding the stochastic graph G. So initially, they only know that they have some item set U, and that there's going to be N buyers which arrive. In addition, the seller is given some known distributions, and it's told that buyer VI is going to be drawn from DI independently in each round. Okay, so formally, we think of having a known ID input, and this includes what we'll call a type graph, and DI is supported on the vertices B within this type graph. So each type node is specified by edge weights, edge probabilities, as well as an integer patience, and you can think of this type graph as representing the possible buyer profiles of the online arriving buyers. Okay, so finally, the buyers actually arrive one by one based on some ordering pi, and pi is either going to be adversarially generated or uniformly random. When a buyer arrives at time t, the seller learns the type of the buyer, as well as the distribution that the buyer was drawn from. At this point, the seller gets the probe at most LB buyer item pairs or edges. Once again, it has to respect commitment. And as in most bipartite online matching problems, once the seller moves to the next buyer, it can never return to the previous one. Okay, so it outputs a matching M of G of active edges. And once again, its goal is to maximize the expected weight of the matching. And so, okay, so that's the objective of the online seller. what do we benchmark against? Well, the most natural thing to look at would be to compare the seller's matching to the expected weight of an optimum matching. But this happens to be too difficult, okay? So the reason is very simple. There's this graph one can consider where there's k offline items and a single online buyer, where all the edge probabilities are 1 over k, and the patience of the buyer is 1. So in this setup, the best an online seller can do is 1 over k, and yet the size of an optimum matching tends to 1 minus 1 over e as k tends to infinity. Okay, so what the standard of the literature is to instead compare the online seller to the optimum offline seller, which we'll refer to as the adaptive benchmark. Okay, so the adaptive benchmark is given all the buyer types of G in advance, and it can probe the edges in any order. It doesn't have to follow any kind of vertex ordering on the buyers. It can jump from edge to edge between different buyers. Okay, so it's to note its performance on the graph G by OpG. Then what we're going to do is average its performance over G, which is drawn from the known ID input. And we'll write this out by the expected value of opt of G. Okay, so then the objective of the problem is to maximize the following competitive ratio. So if the seller returns a matching M, then we look at the expected weight of the matching divided by the performance of the adaptive benchmark. Okay, and so either V is going to arrive in adversarial order or random order, depending on the problem we're interested in. Okay, so how does this relate to other online bipartite matching problems? Well, the first thing to notice is that, okay, if all the edge probabilities are binary, then probing isn't necessary, and the adaptive benchmark is really just the optimum offline matching. What does this mean? It means then that we're actually generalizing the profit inequality matching problem when the arrival order is adversarial, and we're generalizing the profit secretary matching problem when the arrival order is uniformly at random. If the distributions are all identical, so there's some fixed distribution where each buyer is drawn from, then this is really just a popularly studied problem called the online stochastic matching problem with known IID arrivals. And the thing to recognize here is, since the distribution is fixed, the arrival order is irrelevant. Okay, so what's our first result? Well, if we work with adversarial arrivals, then we show that there exists an online probing algorithm which gets competitive ratio 1/2 against the offline adaptive benchmark. Okay, so how does this relate to other results? Well, it generalizes the competitive ratio of 1/2 due to Alea et al. From probably 10 years ago or so now. What we know is actually that this result is tight because 1/2 is actually tight for just the single item profit inequality problem. The other relation is to the stochastic matching problem with known IID arrivals. And here we improve upon the previous best competitive ratio of 0.46, we actually allow for a known ID distributions as well as adversarial arrivals. Okay, so our next theorem is in the context of random order arrivals, and here we actually get an online probing algorithm whose competitive ratio is 1 minus 1 over e. So similarly to the previous classic result described, we generalize the best known result for the profit secretary matching problem of 1 minus 1 over e from a few years ago. And once again, we actually again improve on the 0.46 result that held for known IID arrivals. Okay, what are some additional implications of theorem 2? Well, let's consider the case when all the distributions are point mass. So DI is supported on a distinct vertex of the type graph. So in this case, the graph G is actually known up front to the online probing algorithm. So we call this the known stochastic graph set. All our algorithms are polynomial time in G. And so we actually attain a 1 minus 1 over e approximation ratio against the adaptive benchmark. So this offline kind of bipartite matching problem has been studied a fair amount, and it improves our 1 - 1/E result improves on a recent 0.426 approximation ratio from EC 2022. However, the caveat is that the algorithm in this paper allows for random order edge arrivals, whereas ours requires the online vertices um, to arrive in random order. And finally, let me mention one more kind of generalization of past results. There's a paper from SOTA 2019, which studied the special case when the graph G has unbounded patients. So in other words, any online vertex can probe as many edges as it likes. This is also called the query commit problem. And in this paper, kind of the main result is 1 - 1/E approximation ratio against the adaptive benchmark. And so we can view theorem 2 as generalizing this result both to known ID arrivals as well as to arbitrary patients values. Okay, so for the remainder of the talk, I'm just going to focus on the known stochastic graph setting. So we can always assume that the online probing algorithm has access to G. And before we continue, I'm going to just indicate a generalization that we'll work in. So so far, I've only talked about patience values. However, when we started working on this paper, we were interested in, does the problem become more challenging if you look at other probing constraints? So in particular, suppose I have non-uniform probing costs. In other words, every online vertex has a budget and edge probing costs where I can probe a selection of edges provided the cumulative cost doesn't exceed the budget. Okay, so that was our motivation. The way we come up with a generalization for this is we look at the set of all strings that one can construct from the adjacent edges of V. And then we just define a online probing constraint to be a collection of sequences of edges. So that's what this script C of V guy is. And what this family of strings indicates is which sequences of edges can be probed. So we'll put a sequence of edges within script C of V, if and only if the edges of V can be probed in order of index. Okay. So in this work, we focus on the case when script C is downward closed, which just means that if a sequence of edges can be probed, then any permutation of those edges or any substring of those edges can also be probed. Okay, so what are the techniques that we use in our paper? Well, the first thing that we need to do is we have to come up with a relaxation of the adaptive benchmark. So we do this by considering an exponentially sized LP, whose optimal value we denote by LP opt configure of G. Okay, so there's a number of definitions and notation here, but for a sequence of edges, QV is going to be the probability that all the edges of V are inactive, and val of V is going to be the expected weight of the first active edge of V. Okay, finally, we also just need some notation indicating a prefix of bool D. And finally, in order to describe the LP, we need a decision variable for every vertex and every possible sequence of edges. Okay, so based on these definitions, the objective looks as following. So you can think of XV of E as indicating the likelihood that the adaptive benchmark will probe the edges of E in order. And then, as you can see, we get this objective where for every vertex, we sum over the expected weight of the match of the edge matched to V. Okay, the next constraint is, we'll refer this to as a distributional constraint, and as we're going to see, it's going to allow us to recover a probing strategy from an LP solution. And finally, we have a more standard ex ante kind of constraint where we impose that every offline vertex is matched at most one in expectation. Okay, and finally is non-negative. Okay, so in this work, we prove that the committal benchmark is upper bounded by the LP solution. And what's sort of interesting about this LP is it differs than previous ones in the literature, where instead of having tons of variables, they just assign a single value for every edge, where you think of XV as being the probability the committal benchmark probes an edge. The nice thing about the previous LPs is they're easily proven to be relaxations, but the downside is that it's actually kind of hard to round a feasible solution into a probing strategy. So RLP is different in that the actually proving that it relaxes the adaptive benchmark, so the above statement, is actually quite challenging. But its benefit is that once you solve the LP, it's easy to recover a feasible probing strategy. And moreover, it handles general probing constraints just as easily as patience values. Okay, so how do we prove this statement? Well, the natural thing, based on the kind of loose interpretation I gave of the LP, is that I want to consider the matching returned by the adaptive benchmark, and I'll define the decision variable to be the likelihood that the committal benchmark probes the edges of E in some order. So it doesn't have to be exactly contiguous, just that EI is probed before EI plus 1. The issue with this interpretation is that, in fact, the LP's objective won't actually match up. So we won't get this equality. And this is really due to the fact that the committal benchmark can actually, or rather the adaptive benchmark can jump from vertex to vertex. It doesn't need to probe all the edges adjacent to V in contiguous order. Okay. Other decision variable interpretations fail by violating constraints. So for instance, the distributional constraint might be violated. And the way we kind of get around these technical issues is we introduce what we call a relaxed stochastic matching problem. And the optimal solution to this probing problem is going to upper bound the value of the adaptive benchmark of G. Okay, so in this problem, the relaxed benchmark follows the same rules as the adaptive benchmark, but it only needs to return a one-sided matching of the online vertices. In addition, we impose that each offline node can be matched at most once in expectation. So for a particular instantiation of script n, there might be multiple edges adjacent to an offline node. However, if you average over the performance, the ex ante guarantee is going to be in most. And what's really nice about this relaxed problem is that the benchmark is much simpler to describe. So it's actually, you can prove that it's a non-adaptive. And what this means is that its probes are determined independently of the edge states of G. Okay. And using this property, we can actually exactly characterize our LP in terms of the value of the benchmark. And what that means is then that we can upper bound op G by LP opt of G. Okay, so how are we going to actually make use of this LP? Well, one thing, we have to discuss how to actually solve it efficiently. And despite its exponential size, this can be done assuming we have access to a membership oracle. So in a single step, we can determine whether the sequence of edges is in fact a member of the probing constraint. And yes, the way this goes is we take the dual of the LP, and then we show that the dual has a polynomial times separation oracle. And yeah, so this separation oracle is really due to a previous paper that we wrote from last year's APPROX, and it really reduces to designing a greedy probing algorithm for a fixed vertex. Okay, so we've described the relaxation. We've described how to solve it efficiently. How do we actually make use of it? Well, you can imagine first computing an optimal solution based on the input graph G. And we're going to define a routine called vertex probe, which inputs the sequences adjacent to a fixed vertex and draws a sequence of edges with probability suggested by the decision variable. It then probes the sequence of edges in order and returns the first active edge it finds. Okay, so based on this subroutine, here's the kind of natural algorithm which we'll call basic probing. So you input a stochastic graph, you output a matching of active edges. You first compute a solution to LP config. And then we process the vertices of the only vertices in the order pi. And when a vertex S arrives, we execute vertex probe as described above. Okay, so then this is going to potentially return an edge, and we'll just match it to the corresponding offline node if possible. So unfortunately, this algorithm actually obtains no constant competitive ratio for adversarial arrivals, only a half competitive ratio for random order arrivals. So we have to modify it to prove theorems 1 and 2, even for the known graph case. Okay. So the first thing to observe is that when vertex probe executes, it returns an edge if and only if it's the first active edge adjacent to V that's probed. In this case, we say that V commits to U, and we encode this by the indicator random variable Z UV. And so what we notice is that the probability that this indicator random variable is 1 is related to the following quantity, which we call an edge variable. And then by the ex ante guarantee of our LP, we actually know that the sum of these values is at most 1. And they match up with the LP's optimum value. Okay, so in order to prove theorems 1 and 2, it suffices to show that the probability that the edge is added to the matching, conditioned on Z of E being 1, is at least alpha, no matter which edge you look at, where alpha is a half for adversarial arrivals and 1 minus 1 over E for random order arrivals. Okay, so what's the trick? Well, if we fix an offline node and we define little z of uv to be the probability the random variable is 1, then as described, okay, the sum of these z values is at most 1. And the other observation is that the random variables z uv are actually independent. So this really suggests using a contention resolution scheme. And so a contention resolution scheme for a rank 1 matroid inputs these random variables as well as the vector little z, and it outputs at most 1 random edge adjacent to U, whose random variable is 1. And we say it's alpha selectable or alpha balanced, provided the probability F is a particular edge conditioned on the random variable ZU being 1 is at least alpha, no matter the adjacent edge of U. Okay, so it's an online contention resolution scheme if it processes these random variables in adversarial order, and it's random order if it processes them in random order. Okay, so if the offline vertex U executes its own alpha selectable OCRS as basic probing runs, then we'll get the guarantee that the probability U is matched to V is at least alpha times the corresponding ZUV amount. Okay, so if we have each offline vertex concurrently apply its own OCRS, then we've reduced the problem to designing an alpha selectable rank 1 matroid OCRS or RCRS, depending on the arrival order. And so what's nice is that there's, these things are known to exist. And so for concreteness, we'll actually just, we'll show the one that we use in the paper. So this is due to Lee and Singla. So if we denote the arrival time of a particular vertex by Y of V, then the RCRS is nice and easy. It just inputs the values, and it outputs at most 1 adjacent edge of U. And all it does is that when an edge is presented to the algorithm, it retains it with probability exponential of negative YV times ZUV. Okay, and so what they prove in the paper is that it's 1 minus 1 over E selectable. And yeah, we can actually write an explicit form of our modified algorithm after applying this reduction. So what do things look like? Well, only one line actually changes. So we do everything as we did before, except now, once I run vertex probe and recover a particular edge, if the offline vertex is unmatched, then I won't just add the edge unconditionally, I'll add it independently with the probability right here. Okay, so you can see that, this is like, we could have used any rank 1 minus 1 over e selectable um, uh, RCRS, but the one of Lee and Singla is, it's really quite elegant. So it leads to a really kind of simple modification to our algorithm. Okay, and finally, I'll just mention that the approach is, it's basically identical for adversarial arrivals, and the algorithm written up in the actual paper uses the half selectable OCRS of Ezra et al. From a couple years ago. Okay, I believe that's everything. So thank you for listening.